Now that you know the basics of how ionic bonds are formed and the naming system behind them, we can move on to deeper and more complicated concepts. One of those concepts is variable ions. Variable ions. So what are variable ions? Well, they have to do with the cations that make up ionic bonds. As you've probably noticed, the cations of ionic bonds are always metals, okay? While the anions are always nonmetals. So, and in our previous examples, our cation has been sodium and potassium. Those are both part of the first group, but there's a huge variety of metals that can make up that cation. And most of them are not as simple as sodium and potassium. In fact, most of them are actually variable ions. And variable ions are basically metals that can form various or different ions when they complete their shell. When they complete their shell. Complete their shell. So what does that mean? Well, it's easier to look at an example. So we'll use iron. Iron is right here. Its symbol is Fe. Iron has 8 valence electrons, right? However, 2 to 3 of those valence electrons are actually like willing to leave iron, while the other 5 to 6 stay with iron. So, iron can actually form ions with either a 2 plus or a 3 plus charge. And it can form ions with a 2 plus or 3 plus charge in its ionic bonds. Another example of a variable ion would be tin. Okay? Tin is right here on the periodic table of elements. It has 4 valence electrons. However, when it gives up valence electrons in ionic bonds, it can give up either 2 or 4 valence electrons, and it can be stable either way. This time, tin can form either a 2 plus or a 4 plus ion, okay? So, as you can see, different variable ions have different possibilities for the ions they form. So, which metals are variable ions? Well, it's actually easier to think of them as which metals are not variable ions. And those metals are the first and the second group, so these two columns, and then silver, zinc, and cadmium, which is these three, and aluminum. So these are the only metals that are not variable ions. All other metals are variable ions. So why does this matter? Well, since they can give up different amounts of valence electrons, whenever you're writing out their scientific name, you need to be specific about it. So let's look at some examples of ionic bonds with variable ions. First, we'll use a formula and get the name. So that formula will be Sn₃N₂. Now we can break this down into Sn3, which will be our cation, and N2, which will be our anion. We know that Sn has 2 possibilities for valence electrons that it will give up. So we can't be sure which one it will be. But we know for sure that nitrogen is right here on the periodic table of elements, and it will always have 5 valence electrons if it has a net charge of 0, which means that it will always create ions that have a charge of 3 minus when it completes its shell. And we have 2 nitrogen atoms, so that means we have 2 times 3 minus, and our nitrogen atoms will have a total net charge of 6 minus. And we know that ionic bonds have to have a balanced charge, so the tin atoms have to have a net charge of 6 plus. And we have 3 tin atoms. So we can set up a basic equation. 3 times our mystery charge, I'll just label it as X, is equal to 6 plus. And we can easily calculate that our X is a charge of 2 plus. So these tin atoms are giving up 2 valence electrons. All right, so let's rewrite this as a name, okay? So we have our first part, our cation, which is Sn, or tin. And since it is a variable ion, we need to specify how many valence electrons it is giving up. In this case, we know that it is giving up 2 valence electrons. So in parentheses, we will write down in Roman numerals how many valence electrons it's giving up, which is 2, so II. Then we will write the anion, which is nitrogen. However, as we remember, nitrogen is the anion, like I said, so we need to give it an IDE ending. So we change it from nitrogen to nitride. And that is what Sn₃N₂ is. This is its scientific name. Sorry, I can't make a good box. There we go. Now, let's do one more example where we look at, instead of going from formula to name, we go from name to formula. So our scientific name for this one will be iron 3 oxide. Okay? We can break it into our 2 parts, iron as the cation and oxide as the anion. We know that iron is represented by an Fe when we check our periodic table of elements, which we will do right now. So we know that iron is right here on our periodic table of elements. Its symbol is Fe. And our Roman numerals tell us that it is giving up 3 valence electrons. So its charge will be 3 plus. And we know that it is bonding with oxide, which is oxygen. So we can write our O for oxygen. And we know that oxygen has 6 valence electrons, and it will get a charge of 2 minus when it completes its shell. So all we have left is to balance these two. So how do we do that? Well, it's pretty simple, really. We can take 2 iron atoms, which gets us a charge of 6 plus for the cation, and then we can take 3 oxygen atoms, which will give us a charge of 6 minus for the anion. 6 plus and 6 minus balance out, so now we have a balanced ionic bond, Fe2O3. Now, as you've noticed, our formula does not need to specify the number of valence electrons that are being given up, but our scientific name does need to specify. That's because without it, if we were just given iron oxide, we wouldn't be able to figure out if it was giving up 2 or 3 electrons to the oxygen. However, with our scientific formula, like Fe2O3, we can figure out, if we do the math, that hey, oxygen has a charge of 2 minus, and we multiplied it by 3 because there's 3 atoms, so it'll have a charge of 6 minus. Iron, each individual one, has to have a charge of 3 plus for it to balance out. So we can figure out how many valence electrons it's giving up. Now, there's actually an older system of naming where instead of saying like the element and the number of valence electrons, there were specific words that would represent it. For example, iron 3, that's an iron 2. Iron 3 would be rewritten as ferric. So you can really rewrite iron 3 as ferric oxide. And iron 2 would be rewritten as ferrous. Okay? And generally, in those names, you'll see a pattern where the one that's giving up more valence electrons, so in this case, the iron 3, will have the IC ending, and the version of it where it gives up less electrons, in this case, iron 2, will have the us ending, the OUS, but it'll have the same root, which in this case is fer. For example, another one would be copper. It can be either copper 2 or copper 1. In copper 2's case, it would be cupric, okay, so like that. In copper 1's case, it would be cuprous. So just like before, the version of copper that gives up less electrons will have the OUS ending, and the one where it gives up more electrons will have the IC ending. This is our overview of variable ions in ionic bonds.